Okay, so here we go. This video is going to cover lessons 5 and 6. They're relatively simple concepts, and I do believe that they are covered in Physics 11. If they are not, please fire me an email, and I'll go over, and I can go over them in more detail. But now we're going to look at one-dimensional momentum and impulse and one-dimensional collisions in the same video here. So, momentum and impulse. Momentum is a concept that I feel like you guys should be relatively familiar with. One-dimensional momentum. The reason we specify one-dimensional versus multi-dimensional is because, well, here's the formula for momentum. Momentum, P, it'll make sense eventually why that's P, is equal to mass times velocity, except there's nothing weird here with the multiplication. There's no... this is a, well, let's look at it this way. This is a scalar. Velocity is a vector. So when we had a scalar times a vector, it produced for us a vector. So now we've got momentums that are vectors. So just like when we were dealing with kinematics, we got to be careful when these vectors show up in one dimension versus 2 or 3 even. Hopefully that makes sense. So momentum P equals mv. The idea here behind momentum is the amount of motion an object has. So if you think about this in terms of some different objects here, if I have a small object moving slowly, how much motion does it have? Well, you can think about how much motion something has by how easy it is to stop. If I have a small object moving slowly, that's very easy to stop. That's relatively small amount of motion. If I have a small object that's moving very quickly, it might hurt, but it's still relatively easy to stop. You might not enjoy the process. I mean, you can think of it this way. If I took a slingshot and I shot a marble at you, could you stop it? Yeah, you could. Would it hurt in the process? Well, yeah. So we can say that, yeah, this has more motion than this guy does. So this is larger than this. So we can say that, well, the idea of the amount of motion or momentum, ignoring this guy, is dependent on how fast you're moving. But it's also dependent on the mass. If we ignore this middle one here for a sec, and I just take a look at the beginning one versus the ending one, if I rolled a marble at you slowly, you could stop it with minimal effort. If I rolled a car at you slowly, good luck. So even this compared to this, we can see that the larger object has more motion, even though these two might be moving at the same speed. So this guy is also going to be, or have a larger amount of motion than this guy. So what we're seeing here is this idea that momentum is dependent on, or the amount of motion you have is dependent both on how big you are and how fast you're moving. This concept is called inertia. Or your tendency to continue to move. I mean, the most terrifying of all of these examples that we haven't included here is, what if I had a large object moving very fast? It doesn't look... well, the arrow is a little bit larger. This would have the most amount of motion. It's... the car is on the freeway. Good luck stopping the car on the freeway, kind of idea. So we've got momentum, P, is a vector equal to mass times my velocity. It's proportional. The amount of motion is proportional both to the mass and to the velocity. We can look at a few things here. The units of momentum are given to us. Let's take a look here. I'm going to use a different color. This is kilograms. This is meters per second. we had earlier, if we looked at force here, force was mass times acceleration, which, so as far as the units go, I'll get rid of that. The units here were kilogram meters per second squared. Well, this is pretty similar. If I multiply this by a time, so an amount of seconds, we're going to see here that I'm going to get kilogram meters per second, which is the same thing we have here. So there's a concept coming now very shortly where I have this idea that momentum is also equal to a force times an amount of time. So I've got my momentum here is given to us by mass times velocity. We're also going to see here that momentum is equal to a force times a time. Let's flip the page, keep going. We're going to skip example 2 here. And go straight to example 3. We're not going to do example 3 here either. The concept, you know what? No, let's do it. So I want to prove that momentum change equals mass times velocity change. So if I've got momentum, P equals mv, P and V are vectors. If I have a change in P, well, what's that going to tell me here? A change in P is a P final minus P initial. So my momentum final is equal to my momentum initial. That delta hasn't changed. Its meaning still is what its meaning is. Well, what that means is, assuming mass is constant, what I can see here is I've got my mass times my velocity final minus my mass times my velocity initial. I can factor out a mass from both of these things. So this is going to give me my mass times my velocity final minus my velocity initial. So now what I'm going to get here is that my change in momentum is going to equal my mass times my change in velocity. And this is going to become a little bit more difficult to deal with when we start looking at 2 dimensions, but that's okay. So we've got this idea that a change in momentum is equal to my mass times my change in velocity, assuming my mass is constant. It won't always be, but we're going to operate under that assumption now for the time being. And we're going to jump ahead and we're going to look at this idea. Net force times a time equals a mass times a change in velocity. And I've already kind of made a hand wavy argument about why this is the way it is. Even just by looking at the unit analysis here, a force is newtons times seconds. A newton was a kilogram meter per second squared times seconds. Well, I can cancel an s on top and an s on bottom, so what I'm going to get here is a kilogram meter per second. Well, that's a mass times a velocity here, and so what we can see here is that a force times time has to be equal to a mass times a change in velocity. This particular relationship here is impulse. Is the idea behind impulse. So we'll sum this up by saying the impulse, F net times a change in time, is equal to mass times a change in velocity. So this idea of impulse here is that impulse is a measure of the change in velocity. It's momentum change. And you can use either side of this equation to deal with impulse. So let's just use look at an example here, and this will make, I think, a little bit more sense. So if I've got a 125 gram baseball moving east at 150 kilometers per hour, hit by a baseball bat, obviously the direction of the ball is going to change. The ball is on the bat for 0.075 seconds, very small amount of time, and leaves the bat moving west. It was going east, now it's going west. And its speed is 92 kilometers per hour. We want to find the net force and the direction on the ball. So we could use kinematics and dynamics. We could use kinematics to find the acceleration, and then we could use dynamics to find the force. But I want to show you that we can do the exact same problem using momentum instead. So let's take a look at this. I'm going to draw my problem. I have a bat. I have a baseball. The baseball is going that way. It strikes the bat and now is going that way. There's my V initial. There's my V final. So let's take a look at this thing here. My V initial, we are told, is 150 kilometers per hour. We're going to change that immediately into meters per second. So to convert from kilometers per hour into meters per second, we divide by 3.6. So what this is going to tell me is that 150 kilometers per hour is 41.67 meters per second. And over here, we're going to do the exact same thing. Divide by 3.6. And we're going to convert 92 kilometers per hour into 25.56 meters per second. So my initial velocity is 41.67 to the right. This guy's to the left, so now my velocity here is negative 25.56 meters per second. And I want to find the net force in the direction on the ball. So we can use our impulse equation here. Instead of using kinematics and then dynamics, we can use this equation here. So we know that a force times a time, change in time, is equal to a mass times a change in velocity. Based on looking at those sets of units. If you want a further proof, I can give you one. So let's use what we've got. We want to find a force. We know that the length of time, do we know the length of time? We do know that the length of time that the ball was on the bat was 0.075 seconds. So that's going to be the length of time our force acted. The mass of the ball didn't change. We had a 125 gram ball. We have to give that in kilograms, 0.125 kilograms. And this, delta V, is a V final minus a V initial. So we're going to write it in there exactly as we've got it. Our final velocity was negative 25.56 minus our initial velocity of 41.67. So if we go through and we solve this thing, we're going to get 0.125 times 56 minus 41.67. So this is how I've set it up on my calculator. The right-hand side of that equation is equal to negative 8.40. Negative 8.40 divided by 0.075. We get a force here of negative 112.05 newtons. So what does that tell us? Well, that tells us that because the force is negative, this thing has to be acting to the left, or in this case, west. Called that way positive. So this force is acting about a force of 112.05 newtons west. Forces are vectors. They need to have directions, just like we use the velocities here. So again, we could use kinematics and dynamics, or we can use this idea of impulse here. Let's look at another one. Conceptually, the reason that impulse is necessary to look at, or the ideas behind it are necessary to look at, is because they are used for analyzing collisions, and in the grand scheme of our world, collisions are important. So things like how you design safety measures in a car to prevent people from, seriously injuring themselves when they're in a car accident. That whole argument is based around impulse. And to prove that to you, let's look at a relatively simple example. If I got two eggs dropped from the same height, one hits the floor and then breaks, the other one falls into a pail of water and survives. Why? Why is that true? Well, you could argue a few things. One of the arguments you say, well, the floor is harder than the water is. Yeah, well, that's true. What does that do for you, though? Why does that ultimately matter? Well, here, hopefully you've had a chance to think about this one. Pause the video, think longer if you'd like, but here's the answer to this question. The idea here is that the length of time here is very short. While to bring it from whatever velocity, so impact v, to 0. If you look at these guys right here, the impact velocity here, where it strikes the water and where it strikes the floor, are going to be exactly the same because the ball, or the egg in this case, was dropped from the exact same height. So these two impact v's are the same, but they have to be brought to 0. This particular egg has a longer time to have that velocity brought down to nothing. We're going to compare these two guys here. There's a short time here, a long time here. Well, what does that do? We can look at the change in speed here using momentum. So if I've got here my momentum, and at this point here, at the moment of impact, my momentums are going to be exactly the same here. I'm going to have m v impact and m v impact, and they are exactly the same because my velocities at this point are going to be exactly the same. And we're going to assume that it's the mass of the egg is basically the same here as well. What's happening, though, is as we extend the amount of time, we're decreasing the amount of force on the egg to slow it down. And it comes from this impulse equation here. If I look at Ft equals m delta v, my impact velocities are exactly the same. My final velocities are exactly the same. Final velocity here is going to be 0. Final velocity of the egg here is going to be 0. So these two are exactly the same. Let's hopefully that argument makes sense. So that one and that one are the same. But this t value is bigger, while this t value here is smaller. So let's see what that does to the force. Here I've got F equals, solve for that, delta V over T, and this is going to be F equals M delta V over T. If these two tops are the same, and these two times are different, this one's smaller, this one's larger, I can show you using values. I don't know, let's say that this momentum here was 10 kilogram meters per second, and this one was 10 kilogram meters per second, but this one takes, I don't know, 0.1 seconds, sorry, 0.01 seconds to stop, and this one takes, I don't know, a half a second to stop. Look at the difference here. 10 divided by 0.01 is 1,000 kilogram meters per second squared. 10 divided by half a second is 20. So by increasing the time to slow down, we can see that the force is smaller because it's changing the momentum over a larger period of time. So we have this idea that the egg can survive by allowing it to be brought to zero over a larger period of time. This is the same concept behind airbags. Without an airbag, your face gets stopped by the dashboard in a very short period of time. With an airbag, your face gets stopped over a much longer, well, relatively speaking, a much longer period of time. So your face can still remain your face. So that's why we look at this idea here of impulse. Graphically, we can see the same thing here. If we look at a graph of force versus time for the egg hitting the floor, this is what this thing is going to look like. Again, the floor, so the first part of the example. We've got a large force acting over a small period of time. The area here, area of a triangle is half my base times my height. So that's going to be 1/2. The base here is time times the height. The vertical axis is a force. So the area, we can see the area underneath here is the impulse, force times the time. The question here is which of these graphs, A, B, or C, would best represent the force versus time graph for the egg hitting the water? How is that going to change? Well, we've already seen that the egg hitting the water is going to extend the time and decrease the force. So we know it's not this guy here. So let's look at B and C. Which one of these is most representative? Well, you can see here, looking at B and C, the finer nuances of this, well, is this. The idea with the particular examples, we want to make the impulse smaller. The impulse should not be the same. What we've got here is we've got a force acting over, yes, the force has decreased, yes, the time has increased. But if we compare these two areas, the time has gotten twice as long and the height has shrunk by half. So here, actually, this area and this area are going to be the same. So the impulses of these two are the same because the areas haven't changed. And we know that the idea behind slowing the impact down is that the impulse has to be smaller. I just totally screwed that up. I'm really sorry. Let's take a look at this again. We want the impulses to be the same. Because we know that the change in momentum has to be the same. Sorry guys, I definitely just screwed that up. And I don't really want to start over. My impulses need to be the same. I have an impact velocity that's the same. I have a final velocity that's the same, so my change in momentum has to be the same. So that means my impulse has to be the same. The time just changes the amount of force. If we look at what's going on here, these impulses are not the same. The area here is much larger than the area here. We want the impulses to be the same. So this one cannot be true. It's got to be this guy here. The impulses of this guy are equal. We've got a very narrow base and a very tall, skinny guy. We've got a much longer triangle, and this guy's much shorter. The idea here is that, I know, without actual numbers, it's almost impossible to prove. But this one, and again, should this show up on a assessment of some kind, I would give you actual values to figure this out. We want the impulses to remain equal. The longer time decreases the force. This is how those two graphs should be related. Sorry about that, guys. So for this section, what I want you to look at are a couple questions here. I want you to do 2, 3, 4, 2 to 5. And I want you to take a look at question 12. 12 is graphical, except it actually gives you values to look at here. We're also going to take a look at one-dimensional collisions here, because I think those concepts are relatively simple to look at. So we're going to do that now as well. So this is your first part of your homework for this lesson is 2 to 5 and 12. We're also going to look here at one-dimensional collisions. So one-dimensional collisions use the idea that momentum is conserved. So here we go. In the collision below, which vehicle experiences a larger force? We've got a large truck here. We've got a small, what could be a car here. The idea is, or the question is, which one experiences the larger force? Now, if we were in class, we'd have a chance for you guys to have this discussion with each other. But based on my experience, what seems to be the consensus usually when people argue is one of the following two choices: either the car experiences more force, or the forces are the same. And here are the reasons for both those choices. Students in the past argue that the car experiences the larger force because the thing is smaller. It's the one that's going to, like, you think about it in your head. Obviously, this is the one that's going to take more damage. So the force must be larger on this one, is the argument that lots of students make. Other students would say that something like, well, but we've talked about forces being equal and opposite. If I punch the wall punches me back. Or if I have an object sitting on a table, it's not falling down into the ground. It's not being flung up into the air, because the force downwards from gravity on the object is the same as the force upwards of the table acting on that object. And so we've got forces here are equal and opposite. So which is it? Does the car experience the more force, or are they equal and opposite? Well, I'm hoping by you hearing my explanation of the second one, I'm able to convince you, but both of them have to be the same. You can't have a larger force acting on one of two objects in a collision. It's just not possible. If the truck hits the car with 1,000 newtons, the car can't hit the truck with anything less than that. So these things have to have equal and opposite reactions, which is one of Newton's 3 laws of motion. Well, the question is then, if that is true, why does nobody want to be the car and the driver of the car in this collision? Well, let's look at this. If these things have the same force acting on each other, so I don't know, maybe the impact is 1,000 newtons of force on both of these guys. Maybe the truck weighs 10,000 kilograms, and the car only weighs 1,000 kilograms. Let's look at the difference here. If you have 1,000 Newton force from the impact acting on this truck, let's look at what that does. F net equals ma, so I've got 1,000 newtons acting on a 10,000 kilogram vehicle. Obviously that's huge. The acceleration here is going to be 1,000 divided by 10,000, which is 0.1 meters per second squared. Here, I've got F net equals ma still, but now I've got a 1,000 Newton force acting on a 1,000 kilogram car. Well, I'll say 1,000 A. Sorry, that should be an A. So 1,000 divided by 1,000 is 1, so my acceleration in this case is 1 meter per second squared. Obviously my numbers are skewed, but we can see here that the acceleration of my car, slowing it down, is 10 times larger than for my van. The van or the truck or whatever this thing is going to be fine, relatively speaking. It accelerates a little bit. It slows down a little bit due to the impact. The car, on the other hand, experiences a much larger acceleration. So it's less about what forces are acting, it's more about, well, how is that force impacting your moving forward? Obviously, the bigger acceleration is going to hurt you more. It's not about the force being the change, it's about how you're accelerating. So we're going to look at a bunch of these types of collisions. For collisions in a closed system, the contact forces are governed by Newton's third law, so forces are equal and opposite. I'm hoping I've convinced you of this, which implies that the momentum change has to be equal and opposite. So the momentum is the same. Again, it's the impulse that helps the truck survive and the car get obliterated, but that's neither here nor there. We'll talk about that further. The idea here that I want you to grasp, though, is if that my momentum change is equal and opposite. Because my forces are equal and opposite, what I've got here is that the change for momentum for my object 1 has to be equal to the negative change in momentum for object 2. Again, one reason one is positive, one is negative, is just they're acting in two different directions. What this allows us to do is jump one step further and say, well, the initial momentum of my system has to be equal to my final momentum of my system. In a collision, momentum is conserved. It has to be the same at the beginning as it was at the end. So, and the argument for that is this: since momentum change is equal and opposite, system momentum is not gained or lost. It is simply transferred from one object to the other. This means that momentum is a conserved quantity, just like energy is, assuming nothing was acting on it from the outside. Momentum can be conserved, or is always conserved in a collision like this. So let's look at one example of that. If conditions are such that the car and the truck end up at rest after the collision, how can we say that momentum has not been lost for the system? So let's take a look at this. Starting with momentum initial equals momentum final. Let's operate under the assumption that momentum is conserved here. So look, my initial momentum and my final momentum. I have to look at, if I'm looking at the entire system, I have to look at every object in that system initially and every object in that system finally. How many objects do I have at the beginning? Well, I've got 2. So I'm going to have momentum initial truck, and I'm going to add to it momentum initial for the car. So my initial momentum for the truck is going to be mtvt, and my momentum for the car is going to be, I'll call it mc for car and vc for car. So my momentum for the truck is going to be the 2400 times my velocity was 10. The thing you have to remember here is that my momentums are vectors. And so direction is important. This guy has a velocity going to the left. This guy has a velocity going to the right. In this part of my problem, I've assumed that the 10 is positive here. So what I've done is I've implicitly made the assumption that to the right is positive, which means this velocity here is going to be negative. So I'm going to add to it my 1,000 kilogram mass times my negative 24 meters per second of velocity. Well, that's going to be 24,000 minus 24,000 equals 0. So my momentum initially, this is all initial momentum of the entire system is 0. Momentum finally, well, neither of them are moving. So my velocity is 0, which means my total momentum has to be 0 here too. So V equals 0, so P final has to be 0. We've seen that my initial momentum is 0, my final momentum is 0, which is what we wanted all along. The momentums of my car and my truck are equal and opposite to start. And so that sums them together to give me 0. Let's look at another collision. Different kind of collision. So we can use these same ideas here. The law of conservation of momentum, now, we can see that it is conserved, is given to us like this. The sum of my momentums initially have to be equal to the sum of my momentums finally, and what I need to do here is I need to sum up the momentum for all objects. So let's look at an example here. I've got a 30-gram bullet traveling at 250 meters per second, hitting a 5-kilogram wood block. We're told that that 5-kilogram wood block is at rest, and the bullet embeds itself within the block. If the bullet and the block move together after the collision on a frictionless surface, so maybe this is ice, we want to figure out the speed of the block after the impact, and the heat energy created during the collision. So we know momentum has to be conserved in a collision here. Law of conservation of momentum states momentum must be conserved. Because we know this to be true, what we can do here is we can say, okay, my momentum at the beginning has to be equal to my momentum at the end. And we need to address this, or address momentums rather, for every object in the system. At the beginning, I have two distinct objects. I've got my momentum for the bullet plus the momentum for the block. At the end, I can consider those things one object. I've got momentum for the new object bullet block combination. So let's look at this thing. I'm going to add some stuff to my diagram that I'm going to pull out of the question. I've got a 30-gram bullet. So that means I'm going to write it in here. The mass of my bullet is 30 grams. I'm going to convert that to kilograms. It's going to be 0.03 kilograms. The mass of my block was 5 kilos. My velocity here was 0. And my velocity of my bullet, we were told, was 250 meters per second. And those are the units we want, so I'm going to leave it like that. So I got a velocity of 250 meters per second. I got a mass of 0.030 kilograms. I have a velocity of 0 because we're told the thing's at rest, and a 5 kilogram mass. Here, the bullet block combo has a mass of, well, the mass of the bullet plus the mass of the block. This is going to be 5.03 kilograms, and it has some unknown velocity. We're told it moves off together, and so this is actually what we're trying to find here. So let's go through and let's fill this thing in. The momentum of the bullet is going to be given to me by mv. The momentum of the block is going to be given to, I'll say mv1, mv1, or m1v1. Call that object 1. We'll call this object 2. So this is m2v2, and that's going to equal, I will call this the total object because they have become 1. So I'm going to call this m total v total. So m1 v1 is going to be 0.03 kilograms times 250 meters per second plus a 5 kilogram mass times no velocity, and that's going to equal my total mass, 5.03 times v total, which is what we're looking for here, and I guess I didn't have to put that in brackets. So we can see here 0.03 times 250, that's going to be 7.5, plus 0 is going to equal 5.03 v total. So v total is going to equal 7.5 divided by 5.03. It's going to give me a velocity of 1.49 meters per second. So that block is moving off very slowly, which should make sense. The block is much, much larger than the bullet was, so it's going to take a lot more for this thing to move forward than it's going to take for the bullet to stop. If that makes any, hopefully that makes sense. My argument there makes sense. So we found the speed of the block-bullet combination after the impact here. So that's part A. It's using conservation of momentum. Momentum is always conserved in a collision to figure out what that final velocity is. So let's look at the second part of the question. The second part of the question says, I guess this is the third part of the question. C says, so I should say this is B, A and B. So part C here, find the heat energy created during the collision. The implication there is that energy is not conserved, which is interesting. So let's look at C here. C is the, because it's asking for heat energy, the hint there is that we're going to have to use the conservation of energy equation to figure out what E final. We're going to figure out we have to use the conservation of energy equation to figure out if any work was done by heat. If this ends up being 0, then energy will have been conserved. The energy at the beginning will have to equal the energy at the end, and then there was no heat lost, which I'm hoping you guys can see isn't necessarily going to be true. So let's look at this thing. A few things to take note. The height of the bullet doesn't change, and so we don't have to consider potential energy here. If I call this level 0, because the bullet is at the same level, there is no potential energy, so I can not include that. This guy's not moving. Because he's not moving, he's got no kinetic energy, so initially I only have to consider the kinetic energy of that bullet. So energy initial is going to be the kinetic energy of the bullet. We're going to see if any work was done, and this is going to equal the kinetic energy of the bullet block combination. The height of the block also doesn't change. So the KE of the bullet is going to be 1/2 mv squared plus work equals 1/2 mv squared. And let's put in everything we know. We know the mass of the bullet was 0.03 kilograms. The velocity of the bullet was 250 squared. Plus work is going to equal 1/2. We know the combined mass is 5.03, and their combined velocity is 1.49 squared. If you solve this for work, what you're going to see here, and I want you to do that calculation just to verify for yourself that this is true, the work here that is done is going to be negative 931.9 joules. So if work is negative, that means energy is leaving the system. Well, there's only one way energy is going to leave the system like this, and that's in the form of heat and, well, you can say sound. The vast majority of that's going to be heat. So the block is going to heat up like crazy because of the impact. So we can see here that we used conservation of momentum to figure out the total final velocity, and then we used energy conservation, work energy equation, work energy theorem, to figure out that energy, in this case, actually wasn't conserved. We lost energy out of the system. So the lost kinetic energy in this example was transformed into sound and heat. It also could have been the work done in permanently deforming the objects. There's some, because of this now, there's some language here, some terminology that we use. So there's actually different types of collisions. The first type of collision is completely inelastic collisions. The second type are inelastic or partially elastic. And then part 3 is elastic or perfectly elastic. And so these three terms to classify collisions are dependent on what happens to the energy. So in a completely inelastic collision, our objects stick together, momentum is conserved, and there is a maximum loss of kinetic energy. That one's kind of vague. The idea here is that there's a loss of kinetic energy. In an inelastic or partially elastic collision, the masses bounce off each other, momentum is conserved, and there is some loss of kinetic energy. But momentum is conserved still. In a perfectly elastic collision, the masses bounce off each other, momentum is conserved, and kinetic energy is conserved. So in this one here, in the perfectly elastic collision, no work is done to remove energy. What I want you to notice here, though, in all three types of collisions, momentum is always, always, always conserved, and conservation of energy can vary. So let's look at an example of what that means. For the collision below, I want to write a momentum equation, so I want to find the final speed of... I want to write the momentum equation, I want to find the final speed of the 1 kilogram mass, so that guy, and I want to see Well, in this case, it tells me that is an elastic collision. I want to verify if that's true. So at the beginning, these guys are coming at each other. At the end, they're both going off to the right. So we're going to use every collision has a conservation of momentum. So I'm going to use conservation of momentum to figure out how fast that object's going. So I'm going to call this object 1. I'm going to call this object 2. So this is object 1 and this is object 2. So this is 1 initial, this is 2 initial, this is 1 final, this is 2 final. Because they're all separate objects, I have to address the momentum of each one on both sides. So this guy here, my momentum initial is going to be, so I'm going to have M1 initial, P1 initial, plus M2 initial, sorry, that's a V, MV. V2 initial. This is going to equal M1 final, V1 final, plus M2 final, V2 final. Let's fill it in. My mass here is 2. My initial velocity was 7, plus my mass here is 1. Now my initial velocity here is acting to the left. When I put this one in here, my 7 was positive, so this is going to have to be negative because it's acting in the opposite direction. So this is going to be negative 2, and this is the mistake that always gets made. The positives and negatives. You got to be real careful when you're dealing with these types of collisions. So this is going to equal, he's moving to the right, so he is 2 times final velocity of 1 plus 1 times V2 final. We don't know what this is. So let's figure it out. 2 times 7 is 14, minus 2 equals 2, plus 1 times V2 final is just going to be V2 final. So I can subtract that over. 14 minus 2 is going to be 10. So I'm going to get 10 equals V2 final. That's going to be meters per second. So this guy is actually moving at 10 meters per second off to the right. This is parts A and B. So we're going to look here at part C. We'll see what kind. So now we figured out how fast it's going using conservation of momentum. Now we're going to see what kind of what kind of collision this is by looking at the energy. So I want to use energy initial plus work equals energy final. We're going to see what's going to happen here. My energy initial, these guys have, there's a kinetic energy for object 1 initially, plus kinetic energy 2 initial, plus work, if there is work done, equals kinetic energy 1 final plus kinetic energy 2 final. There's no potential energy in this question because the objects aren't changing height above some surface. So I'm going to get 1/2 2 times 7 squared plus 1/2 1 times negative 2 squared plus work equals 1/2 2 times 1 plus 1/2 10 squared. Or actually, it should be 1 squared. So let's do this. Half of 2 is 1, so 7 squared is 49, plus negative 2 squared is positive 4, and a half of that is 2, plus work equals a half of 2 is 1, and 10 squared is 100 times a half is 50. So I get 51 plus work equals 51. I can subtract my 51 over, and we're going to see here that work equals 0. So there is no work done, which tells us energy is conserved. If I go back up here and take a look at what that means, if energy is conserved, I have an elastic collision, so we have verified what we were trying to prove. which is neat. That's the last example out of here we're going to do. I know there's a couple more on the next page, but I'm not going to do them. So I want you guys to go straight ahead and take a look at the following questions here. I want you to look at 2. Do I want you to do all of 2? Yes, I want you to do all of 2. I want you to do question 4. It's another impulse question. I want you to try question 5. And I want you to try question 8. So, 8's really quite a good question. You're going to use momentum and energy. Make sure you draw 8 out really carefully.